Hey everyone, coming up next is Anoop from Deepgram talking about how to learn from leaders, how customers are building production grade voice agents.
Thank you. Thank you, everybody. How many of you here have actually built a voice agent? Okay, couple of people. How many of you have talked to an OpenAI voice bot and had a conversation? Okay, a lot more. Great. So what I'm going to talk about today is how to take that OpenAI experience, make it significantly better, and then use it in your business applications, and what people are already doing with it and what they've learned from it. So first of all, what is Deepgram? Deepgram is a voice AI platform for business use cases. And what we do is we ship transcription, which is speech recognition, speech generation, text to speech, if you will, and then voice agent APIs that are used by developers to build voice agents. So we are not we are not a character AI where you can go and talk to characters. We are a voice agent API built for developers by developers, so you can build a character AI. All right, so let's talk about this journey a little bit. I think speech to text has been around for a really long time, right? But it was fairly terrible, and it was for batch processing. And the primary use case was your call is being recorded for quality assurance purposes. That call would literally get recorded, and in the night, a speech to text transcription service would run, which will convert it all into text. And then you will do textual analytics on it. You would do sentiment analysis. You'll see if the agent followed the prompts properly. You would see who was abusive. Was the agent abusive or the customer abusive? How to train people, so on and so forth, right? That was there for a really long time. And then text to speech was kind of sort of there, but not really. I mean, you've spoken to Alexa a little bit. Uh, but then what happened is two things happened. First is, of course, LLMs came into the picture and thinking was there. And then people started to connect the dots and say, hey, if I can have real-time speech to text and real-time text to speech connected with the thinking system, I can build voice agents. And why are voice agents important? So actually, if you think about what happens in customer support, customer service, or business interactions, there are over 1 billion interactions today, every day, that happen in business that probably don't need a human to do. A lot of it is standard grunt work, following a set of rules, answering a bunch of questions. So that's 1 billion every day. And so if you have an intelligent voice agent, you can replace all of that and create a huge amount of productivity in the world. Let me give you an example. There is roughly about 6 to 700 billion dollars that is spent on this agent system, call agent systems, if you will, and almost all of that is human labor and human spend. And most of the people who are working in that industry have 67% attrition rate. They don't like to work there. So imagine if you can shrink that 700 billion to 100 billion, that's $600 billion in net profits to the bottom line of a lot of companies. So that's why there is a lot of this buzz around voice agents. So I just wanted to set the context on the business side. So anyway, let's get more technical, right? So the first thing people said is in order to build voice agents, the latency has to be super, super low, and the accuracy has to be high. Because if you cannot understand the business jargon that the person is talking about, then how will you be able to serve it? Imagine like I don't know, pick your favorite Krispy Kreme donut or a Popeye menu item. And if you're trying to order it on the phone and the transcription doesn't understand it, then there is no chance in hell that you will be able to serve it. So that was the first step. The other thing with that is the lower accuracy you have on your speech to text, the higher noise you will have in your voice agent. This is no different than, we used to play this game, right, where 6 people stand in line and they talk to each other, and then the 6th person tells you what the first person said. It's the same thing here. So then the second thing is, okay, what was the previous state of latency? When I talked about the call is being recorded for quality assurance purposes, that latency was pretty high. But the human latency is about 200, 250 seconds in terms of how quickly our brain takes a audio and then transcribes it in our brain. So you have to get there. If you can't get there, you don't have a shot. So that was step one, right? So Deepgram is at this point subhuman in terms of its latency and superhuman in terms of its accuracy. So now you got the left side done. The LLM and friends, I call them LLM and friends, but it's the entire cognitive architecture that you surround your language model with to be able to do all the agentic workflows that I'm sure most of you are building. The LLM and friends do the thinking part, or the reasoning part, if you will. But then the next thing is speech generation, which means, okay, I heard your query, I understood your intent. Maybe your intent was to cancel the credit card, and I gave it to my thinking system, and the thinking system has now processed the cancellation, and now I have to express to you that the cancellation has been processed. So that expression part is the speech generation part, and so that also has to be real time and a way in which humans will feel that they're talking to a reasonable voice. And we see the jury split here. We have some customers that say, hey, I need the agent to be robotic. I need the customer on the other end to know that they're talking to an AI system. And the others will say, no, I need it so real that they can't tell any difference. So, there will be many use cases here. Anyway, but here is then what happens. Okay, you have the speech, you have the thinking part, you have the speech recognition part, you have the speech generation part. Are you done? Can you build voice agents? And here's what we have found with a lot of our customers. When you prototype this, you can go to a Cursor, Windsurf, you can specify all these APIs, and you can say, hey, build me a voice agent. And if you kind of know what you're doing, you can build it really quickly, and it kind of sort of works. But what happens is there is very little orchestration or observability. And as soon as you try to put it into production, the customers find out like, oh, the call didn't go as well as planned. What happened? Well, I don't know what happened. Well, there is no data dog for voice agents where you can see the logs. So you have to find out the audios. You have to find out what the customer said. You have to find out what the LLMs did. And then you have to stitch together what happened. So that's one thing that breaks down. The second thing that breaks down is, okay, you fix all of that. You try to go into production. I asked how many of you have talked with OpenAI or Character AI, and you will notice a lot of times what happens is there is a barge in, which means I am talking to the agent, and the agent thinks I'm done and starts talking back. And I'm like, whoa, wait, dude, I'm not done, right? So there is this idea of like the fact that I'm not done talking, the fact that I'm holding my turn is unavailable in these systems, and they can't really deal with it, which makes the experience very janky. And you again get frustrated, just like we get frustrated with current customer support things. Like how many times have you got, I know I've done this, representative, I want to talk to a representative, like repeatedly, right? And that kind of experience is what you want to avoid. So, okay, so you go there, and then you start seeing, okay, I have observability, I have fallback, I somehow have to figure out this interruption detection, barge in, end of thought situation. And I don't know where it fits. So some people use VAD, which is a voice activity detector. And it's basically a simplistic system which says, I'm just going to look for silence. If you're quiet for 400 milliseconds, I'm going to assume you're done. But most of us don't speak as a rattle, right? We pause, we intonate, we think. If somebody even asks me for an ID and it's 7-digit ID, I'll be like 3316758, and I've already put 400 milliseconds of pause in there. So that's another issue that happens. So then you start to scale to production, and then all hell breaks loose. Because again, how do you promise P95 latency for all of these interactions so that every interaction feels real? Voice agents are different than classic agentic systems, because in classic agentic systems, you get a token by token response and you're okay with it. But with voice, it is all real time, which means if I don't hear somebody speaking on the other side or telling me that I'm thinking, give me a second, I think something is wrong, right? And then the other thing that happens is on the production side, if you think about what's happening on the GPU on the inference side, I can't let go of the GPU if I have a call going on. because I have to process the whole thing. But if you're doing this on LLM side and I have thousands of GPUs, I can slice and dice my query across thousands of GPUs. A few GPUs go down, no big deal. I can switch to another GPU. None of us will see the difference because the tokens keep coming in. So it's very different in terms of how to take production voice agent. So what is the next big challenge at this point is the trade-off between interruption and latency. How long do I wait to know that you're done speaking so that I don't interrupt? But if I wait too long, then I create too much latency in your systems. I had a very nice video, which I don't know if it'll play and it'll be loud enough, so we'll see. If it doesn't, we'll skip it. So what ends up happening is, in order to solve the trade-off between latency and interruption, you end up having to build three more components. You need real-time streaming speech to text. As soon as I'm speaking, the words are coming out. The transcription is coming out, so I can give it to the large language model, so it can sort of warm up to know what my intent is, so it can call the functions that it needs to call and generate the response that it needs to generate so that the voice agent works. And then there is the voice activity detection, which I talked about, which is like if you take a common open source voice activity detector, it's going to be, tell me how long you want me to wait, and then I'll say done, right? Versus what you need is a more semantic system, a system that understands when a human is actually done with its end of thought and then interrupt you. And then, of course, the end of turn, like is it done with the end of turn? So this is the iPhone moment, if you will. You need a voice activity detector, you need an end of turn detector, and you need streaming speech to text. You need a voice activity detector, end of turn detector, and streaming speech to text. So this is what production customers face. And so what Deepgram did recently is created Flux, which is the world's first conversational speech recognition detector system, which is a streaming speech to text system. It is a voice activity detector, and it has end of turn detection all built in. And what that does, it helps you now really create artful, seamless conversations in your voice agent without having to worry about the technology and modeling pieces that go under the cover. All right. Time for the truth. The video is not going to work, and even if it works, I don't think you will hear it. But essentially, I'll tell you what it shows. It shows you a demo of really how the interruption comes in and all the problems that happen with a regular voice agent, and how when you replace it with Flux, it's smooth. If you want, you can come upstairs to our booth and we can show you the demo. Or you can actually try it out in real upstairs. So let me tell you what this contribution is. What's the big deal of this, right? So on the bottom is the medium end of thought latency to understand if the speaker is done speaking. And on the vertical is the accuracy F1 score of the end of thought. Like how accurately is it being able to predict? And if you take a VAD, it is just a simple linear line, more or less. So if you look at the Celero VAD, you can see that how clean and simple it is. And then a lot of other people contributed to make this better. In fact, the interesting thing is, if you look at the SmartTon V1 and the SmartTon V2 from PipeCat, you might think that the V2 is worse than V1 because it's below in terms of its accuracy of detection. And you may be right for the two dots that are on the right. But if you look at the yellow dots on the bottom, those dots were not even available in the previous version. So a lot of people are looking for ways to do end of thought accuracy. And so they like V2 because they were able to find at least some ways, even if it's 75% probability of detecting an end of thought. By the way, another simple way to think about it is, if you have 75% accuracy of detecting end of thought, you're barging and interrupting 25% of the time. That means you're going to interrupt the other person 1 in 4 times. It's a fairly terrible experience. So what did Deepgram do? This is the new frontier, right? So if you look at the end of thought accuracy now, it's significantly high. And roughly at around 400, where the arrow is, you get almost 90% end of thought accuracy. Now, How long do you think it takes humans to detect somebody stops speaking? Any ideas? Like 1 second? How many of you think it's 1 second before we know somebody stops speaking? All right. How about 500 milliseconds? How about 250 milliseconds? All right. So there's a lot of research on it. Of course, it's not 100% accurate, but it's about 3 to 400 milliseconds is when human brain knows that somebody stopped speaking. This is no different than when we are driving and somebody slams the brake. How long does it take for us to detect, oh, it's red, the brake is slammed, I need to do something. So I think essentially by directly embedding turn taking, you really get a superior experience. I'm not going to bore you with all the quotes, but people have tried it, they like it is working. And then finally, I will leave you with one thought. For those of you who are in voice, you must have heard a debate between cascaded systems and a full speech-to-speech system. A cascaded system is when you take a speech-to-text, LLM, and text-to-speech, and you stitch it together. So it's cascaded. And a speech-to-speech system is this new model, which would basically do everything all together in one big model. And the promise is if you put them together, you will be able to reduce the latency. And the second promise is if you put them together, you can do some more interesting things. So for example, if I say a word, I might be saying it in LLM and text world, a single word is just a word. A hello is a hello. And it has a token representation in the vector space, and that's that, right? It has one token representation. But in voice, a hello is not a hello. A hello can be said in many, many, many ways. It can be said interestingly. Now, I'm not a voice actor, but it can be said interestingly. It can be said with like, disdain, hello. Or it can be said with excitement, hello, right? So there are many ways to say hello. And so that makes speech-to-speech more interesting because now you can capture the emotion of the person that's saying that thing and then pass it through the whole model so that the response takes into account the emotion. If you do it in the classic cascaded system, what happens is you have to infer the emotion. And sometimes the words we speak have the emotion. Sometimes the words we speak don't have the emotion. So me and my wife, we have a great relationship, but when we were early together and she said, you can do what you want to do, I thought I can do what I want to do. It was a very literal interpretation, but then I learned, right? And that's just me. Like I had to learn how to like listen to people's intonations. But that is very important. What it tells you is that a lot is captured in how we say things that is not captured if you just transcribe. So when you write things down in text, a lot of richness is lost. So that's the promise of speech to speech. And this is why the world is trying to say, hey, you will have cascaded systems for certain applications, and you will have speech to speech system for certain other applications. So let me leave you with a thought here, which is, so here is one representation. We took the same word hello, and we were able to create 15,000 different embeddings for that same word, which means there are 15,000 different ways we were able to come up with about how hello is expressed. Now imagine that for every word, imagine that for every sentence, imagine that for every conversation we are having, and then we can have such a vast, rich, audioscape of how people interact and then respond back with voice agents that truly feel real, empathetic. And these are very useful for other cases. It's not all about business because sometimes what can happen is, let's say you have a call center and somebody calls in and they're not talking about the credit card. They just called in and they start sharing things that might do self-harm to them or to others. Like, how are you supposed to recognize or react to that? Those sorts of things can happen when you have a rich audioscape. So that's the promise of speech-to-speech systems. And so I'll leave you with a thought of where audio and voice agents are going. We are going for an audio Turing test, just like everybody else in the world is going for like a regular Turing test with LLMs. And there were a lot of challenges to climb that hill, starting with voice AI, accurate speech to text, low latency, voice quality, thinking with LLMs that came in, interruption detection, Flux. The next thing is context, passing the context of emotions or intent through the whole system, and finally, achieving the nirvana of audio Turing test. Thank you. If you have any questions, I'm happy to take them.